I'm Brian Dickinson, and this is a training byte on the lock and grab methods for concurrent sequence arbitration in UVM. This is the fourth in a series of training bytes showing you how to use UVM concurrent sequences to create interrupt handling routines. In the first three training bytes, we had a look at simple, prioritized and user-defined arbitration methods. In this training byte, we'll have a look at the lock and the grab methods, which allow us to grant exclusive access to a sequencer for a given sequence. So let's just recap what we're doing here. We are creating three streams of data which are going to execute on a sequencer. We do this by having an increment sequence here, which counts up data items from a starting value given to us by the random sequence property count, and then we execute this 3 times in 3 separate blocks of a fork join in the body of our interleaved sequence. And this creates 3 parallel threads of data which are being passed down to our sequencer. And the sequencer then selects the next data item according to its arbitration method. So let's have a look at the lock and the unlock methods first. Okay, so we can execute the lock from inside of a sequence or from a sequencer by calling it off a given sequence handle. Now when you execute the lock gives that particular sequence exclusive access to the sequencer. Okay, and it keeps that exclusive access until the access is released by the sequence executing the unlock method. Now the key thing about the lock is the lock request is granted through normal arbitration. So I assume here I have a sequencer which is using the SEQ arb FIFO arbitration. This means the items are executed in the order of arrival. We assume here that the order of arrival is top down, so we get item 10 from stream 1, followed by item 20 from stream 2, followed by the lock from stream 3. So again, we execute the items in the order which they appear. We do the 10 first, we do the 20 from stream 2, and then we reach the lock from stream 3. Once stream 3 executes the lock, it now has exclusive access to the sequencer. This means it can continue executing all of its data items, okay, until we get as far as releasing the access using an unlock. Only when stream 3 has unlocked the sequencer can we revert back to selecting the items from stream 1 and stream 2, okay, taking the 11 and the 21. So the key thing about the lock is once the lock is granted through normal arbitration, then the lock grabs control of the sequencer until it is unlocked. So here you can see that all 3 data items from stream 3 appear together in the output of data items representing the lock that stream 3 had. Now the lock and unlock, these are tasks, okay, they return once the lock has been resolved, and we use lock and unlock for sequences which once they have been granted through normal arbitration must run exclusively to completion. Now let's contrast that with the grab and the ungrab. So again, the grab and the ungrab are methods which we can execute from a sequence or call off a sequence pointer from a sequencer. Once you execute the grab, it grants exclusive access to that particular sequence, but the key thing about the grab is if there is a grab waiting in the arbitration queue for the sequencer, it doesn't matter what arbitration method we're doing, okay, we're executing on the sequencer, we immediately execute the grab. So again, we have the arbitration method SEQ arb FIFO for our sequencer. This normally executes items top down. We assume the order of arrival is top down here for the items, but now because we have a grab waiting to be executed, the grab is immediately executed. The grab bypasses any arbitration to immediately grab control of the sequencer. Once we've grabbed control of the sequencer, we're going to complete all the items of stream 3, okay, in the order in which they appear until stream 3 unlocks the sequencer by executing ungrab. Once it's ungrabbed, we can then go and execute the items of stream 1 and stream 2 in FIFO order as before. Once the grab is released, we revert to the normal arbitration mechanism of the sequencer. So again, grab and ungrab, okay, these are methods. They will return, okay, once the lock has been resolved, and we use grab for sequences which once triggered must run immediately. So for example, we can use these for simple interrupt handling. Now be careful, okay, you can have multiple locks and grabs in the queue of items pending for a sequencer. Now these are tasks which only return them when they are resolved, so there's no priority on locking. Okay, if one sequence currently locks the sequencer, you can't execute a pending grab, for example, until the first sequence is unlocked. So a new grab or a lock is only granted if there are no other grabs or locks in effect. If there is a grab or locked in effect, then the new request is queued until the arbiter is unlocked. And again, queued lock and grab requests are resolved in strict FIFO order, regardless of the arbitration scheme the sequencer is currently using. So again, we have seq arb FIFO here for my sequencer. Executes items in the order of arrival. I assume the order of arrival is top down. Okay, so first of all I execute the lock of stream 1. This immediately grabs access to the sequencer and executes the whole of the stream 1 sequence until stream 1 is unlocked. Then normally, according to the arbitration FIFO scheme here, we would go to stream 2 and execute the 20 because that arrived next. But because we have a lock pending, we immediately execute the lock of stream 3. So this goes next straight away. It means that we then execute all the items of stream 3 until stream 3 is unlocked, and only when stream 3 is unlocked can we process the items of 20. Okay, so this byte covered locks and grabs, and remember the distinct difference is that locks are granted according to the current arbitration scheme, whereas grabs are granted immediately regardless of the arbitration scheme. In the next and the final byte in this series, we'll show you how we can build up this information we've learnt over the past training bytes to handle simple and prioritized interrupts in UVM.